Okay, last thing we need to do to wrap up these two chapters is to calculate heat in chemical changes. So far we've been focused on physical changes, changing from one state to another, dissolving things in water. Now we need to look at chemical reactions and how heat is involved in those. So what we need to look at are called thermochemical equations, not just chemical equations, but thermochemical equations, meaning you include the amount of heat that's involved in the reaction in the equation. So, for example, if you mix calcium oxide with water, an exothermic reaction takes place. So here's what happens. Solid calcium oxide reacts with liquid water to produce solid calcium hydroxide, and at the same time 65.2 kilojoules of heat are also produced. So having the heat on the product side of the reaction makes it an exothermic reaction because that amount of heat is being released by the system. Now we could also say that the delta H of the reaction, Rxn reaction, is negative 65.2 kilojoules. Remember that negative means heat is released. Now it is important that you include the physical states in your balanced equation because changing states will include some amount of heat. So you have to make sure that here we're talking about liquid water and not ice or steam because that would change the amount of heat because making that phase change involves heat as well. So make sure you include the physical states and pay attention to the physical states. All right, another example. Baking soda decomposes when heated, releasing carbon dioxide. So when something decomposes when heated, that means it's going to absorb heat in order to decompose. So this would be an endothermic reaction. And here's baking soda, 2NaHCO3 solid, absorbs 129 kilojoules of heat to make sodium carbonate, steam, and carbon dioxide gas. So because the heat is on the reactant side, it is an endothermic process, or it has a positive value for the heat of reaction. Now, we can use our heat of reaction again as a conversion factor. So, how many kilojoules are required to decompose 2.24 moles of sodium hydrogen carbonate? So, start with what we're given. Over 1. Now, our heat of reaction, since it's in the balanced equation, we can think of it like part of the balanced equation, meaning we're basically doing kind of a kilojoule to mole ratio like what we did in stoichiometry. So, 129 kilojoules for every 2 moles of NaHCO3. So that number of moles comes from the balanced equation, just like a mole ratio does. So you have to pay attention to that balanced equation when you're making your conversion factor for heats of reaction. They're not per mole like all the other ones we've seen with physical changes, like changing from solid to liquid or liquid to gas. So here when we do our math, we end up with a grand total of 144 kilojoules are required. Okay. Now another specific type of heat of reaction would be called the heat of combustion, and it's specifically for the complete burning of 1 mole of a substance. Okay, so combustion reactions, things burn in oxygen to make carbon dioxide and water. This is the heat that goes along with that combustion reaction. So delta HCOMB for combustion. How much heat is released when 12.5 grams of ethanol burns? Okay, so we're going to start with what we're given, 12.5 grams of ethanol, which is C2H5OH over 1. Okay, now the heat of combustion is the number of kilojoules for 1 mole of the substance. So this is kilojoules per mole of ethanol. We have grams, which means we need to convert to moles. So we need the molar mass of ethanol. From the periodic table, you would add that up and get 46.068 grams of ethanol per mole. Grams cancel. Now we can use our heat of combustion, 1235 kilojoules per mole. So our moles cancel, and when we do that calculation, we get 335 kilojoules of heat released, so those need to be negative, when 12.5 grams of ethanol burns. So that's how you would use the heat of combustion. Okay, now we want to look at how can we calculate the heat of a reaction when we can't actually measure it? And there are two ways we're going to do that. One is called Hess's law of heat summation. And basically, Hess's law says that if you add two or more thermochemical equations to give a final equation, then you can also add the heats of reaction to give the final heat of reaction. And I'm going to show you what that looks like. Now, when we're doing Hess's law, we do have a couple of rules to follow. One says, if a chemical reaction is reversed, the sign of delta H is reversed, meaning if you have an endothermic reaction, if the reaction was flipped and went backwards, it would now become exothermic. And the second rule says that if a chemical reaction is multiplied to change all coefficients, the delta H is also multiplied. So if we double everything in the reaction, we would have to double the amount of heat supplied or released by that reaction. Okay, so this works best if we work through an example together. How much heat is released when diamond turns into graphite? This is not a reaction that we could do. It is very, very slow happening, and it happens at super high temperatures and pressures. So it's not really a reaction that we could do in a calorimeter and measure the change in temperature and calculate the heat. So we have to use another process in order to figure out the heat involved in that reaction. So what we do know is the heat of combustion for each type of carbon, and this comes from a table in your book. Heats of combustion are given. So to combust diamond with oxygen to make carbon dioxide, this is how much heat would be released. To combust graphite with oxygen to make carbon dioxide, this is how much heat would be released. Those things we do know. So we're going to use reaction A and reaction B to come up with this overall equation that we're trying to find the heat of. So here's how we have to do that. When you look at these two reactions, A and B, okay, we can do two things to them according to our rules. We could reverse them and we can multiply them. Now, if you'll notice in our overall equation, we want graphite as a product. In equation B, graphite is a reactant. So we're going to have to take equation B and reverse it. So here's what that looks like. When we reverse reaction B, CO2 gas yields graphite plus O2. Our delta H now becomes a positive value. Okay, so now that we have a new reaction B with graphite as a product, we can add reaction A to reaction B and look what happens. So when we add these together, we have diamond plus O2 yields CO2, and CO2 yields graphite plus O2. O2 shows up on both sides of the arrow, so when they add together, they get canceled out, just like you do in math when you add equations together. CO2 also is on both sides of the arrow, so it can get canceled out. So our overall reaction that we end up with, carbon, diamond, yields carbon, graphite. Now, when we add the reactions together, we can add the delta H's together. So our overall delta H for this reaction ends up being negative 1.9 kilojoules. So we were able to figure out the heat for a reaction that we couldn't do using reactions that we did know the heat of and combining them together. That's Hess's law. Now, the other way we could figure out the heat of a reaction when we can't measure it is to use the standard heats of formation, which is delta HF. The standard heat of formation is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. Now, there is a chart of heats of formation in your book on page 316. And if you'll notice in that chart, all the heats of formation for free elements are 0 because you don't have to make them. They're not compounds. They already exist that way in nature. So there is no formation of an element. So the formula we're going to use to find the heat of the reaction, we're going to add up all the heats of formation for the products and subtract the heats of formation for the reactants. So let's work through an example. What is the heat of reaction for the reaction of carbon monoxide gas, CO, with oxygen gas, O2, to produce carbon dioxide gas, CO2? Now we want to balance our equation, and then using the chart on the page that was on the previous slide, we can look up the heats of our reactants. So the delta HF for our reactants is going to be 2 times carbon monoxide, which is negative 110.5 kilojoules, plus 1 times oxygen, which is 0 kilojoules. When we add all of that up, we get negative 221.0 kilojoules. Then we want to figure out the heat of formation for our products. So for our products, we have 2 times carbon dioxide, which is negative 393.5 kilojoules. And when we multiply that, we get negative 787.0. Now, to find our heat of reaction, we're going to take products minus reactants. So, negative 787.0 minus negative 221.0, and that's going to give us a grand total for the reaction of negative 566.0 kilojoules. Is this endothermic or exothermic? That negative tells us that it is exothermic. Okay. Last few things. There are two different diagrams that we can use to show the overall chemical or physical process and the heat involved. So if our energy diagram has reactants high energy and products low energy, that means it's exothermic. The energy is being released as that reaction progresses. The opposite, if the reactants have low energy and the products have high energy, then our delta H is going to be positive, meaning it's an endothermic reaction. Now, you could also see enthalpy diagrams that look like this. Reactants down here, products over here. So that would be our delta H. Here, our reactants start high, products end low. So this would be our delta H, meaning the heat is released. So you can find the delta H by looking at the difference between products and the reactants and know if it's endothermic or exothermic. For example, the formation of carbon dioxide from its elements can be shown using the following enthalpy diagram. So here are the elements, here's the product, our delta H is negative. So is this an endothermic or exothermic reaction? It is exothermic because the products have less heat than the reactants. Heat was released. Last example, write a balanced thermochemical equation using the diagram below. Okay, so here are our reactants, N2 plus 3H2, and then our products, 2NH3. Now, where would the heat go? So the reactant started up here, the product ended up down here. Was this many kilojoules released or absorbed by the reaction? Well, if the reactants had higher heat than the products, that means that this amount of heat was released. So we would say plus 91.8 kilojoules on the product side. So it released heat, meaning it is exothermic.